All right, good afternoon. Apologies about the Wednesday video. I couldn't manage to fit it in, but my plan now is I've already copied my annotations over to the notebook. So there's quite a few equations and stuff that we have to go through. So I'll go over so the annotation is already there, my writing is already there, everything's available to the students, and I'll be able to do a better job of like going through in class the explanation. And so we'll cover a big chunk today, and then a little bit extra on Monday, and then by Wednesday we should get fully caught up back again. All right, so let's okay. We stop here. We determine the operating mode for a transistor. All right, we'll look at an example. Now, depending on the operating mode, we can model the transistor. And here we are showing a few large signal models. Okay. There's analysis where we say it's large signal and small signal. We talk about that later. Small signal essentially is like we treat many of the AC signals that are small, millivolts or small. Basically, it affects the transistor on the input side in a very small amount. And large signal would be anything that's larger than, like, say, 50 or 100 millivolts. Okay. So large signal models, we have three modes of operation: cutoff, saturation, and active. In cutoff mode, both junctions are reverse bias. Both junctions are reverse bias. The emitter does not emit any carriers, does not generate any free carriers. And so both junctions are off. Hence, the transistor is in cutoff mode. At that point, we can model the base junction as an open circuit. If you model the base junction as an open circuit, IB, for all intents and purposes, is completely equal to 0, except for a small reverse saturation current, obviously. But there is a very small, tiny amount of current that flows from the collector to the emitter, and that is on the order of, or very similar to, the saturation current or the leakage current. Okay, so it's very, very small, and it's referred to as ICEO, collector emitter current, when the base is open. The O stands for open. So there's ICEO. In cutoff mode, we can use a model where we have a current source with a value of ICEO between collector and emitter. In the saturation mode, both junctions are forward bias. The voltage drop across both junctions are constant. VBE is, of course, is constant at V gamma. V gamma is what our author uses to note the forward voltage drop across the junction. Typically is about 0.6 to 0.7 volts. And then in saturation, when the collector emitter junction is forward bias, collector base junction is forward bias, VCE drops to a level of 0.2 volts or less. Right, 0.2 volts or less. And so on both sides, we have a constant voltage drop. On the input side, we have 0.6 to 0.7 volts. And on the output side, we have VCE. Okay. And then the most important mode, application as an amplifier, takes place in the active region, the active mode of operation. The base emitter junction is forward bias, so it's still modeled as a voltage source. But on the output side, the current is not saturated. The current is a function of the input current, IB. So IC, which flows from collector to emitter, is a function of IB. The equation is beta IB. And because IC is not saturated, it increases or decreases linearly as a function of IB, the base current. And the constant of proportionality would be beta, the current gain. In the saturation mode, the equation IC is equal to beta IB doesn't hold true, because if it's saturated, then the ratio could be anything. IC would be constant, right? IC is at a constant level, it's at a saturated level. So even if we change IB, whether IB increases or decreases at that point, IC remains saturated at a fixed level. So this relationship, IC is equal to beta IB, is not true or not valid in saturation region. Okay. All right. More importantly, in the active region, we can model IC as a current source, right? But it's a current source that is dependent on the value of IB from the input side. Hence, we model we model IC, the collector current, as a dependent current source. The dependency is on IB. Does that make sense for the large signal models? Yes. Yeah. 50 to 100 millivolts, yes. No. So AC, so the question being asked is what is considered as small signal? Small signal is basically the input AC signal that we apply as a input to any circuit. So whether it's a diode or whether it's a transistor, a signal that's about, 0.1 volt, 50 to 100 millivolts in amplitude would be considered as small signal. In general, that's what is considered as small signal. As an example, if we remember the lab, I think it was lab 3 or 4, where we built a CE amplifier and we reduced the input signal by using a voltage divider network or voltage divider circuit at the front end. We were reducing it down, making it smaller. The reason we were making it smaller because the gain of the amplifier was very large. If the input was large, the output would be correspondingly larger, but it would drive the transistor into saturation and cut off. And so we made the input signal smaller so that when it amplifies, it does not go beyond the bounds of our voltage supplies. And so that would be considered as a small signal. We applied and I think we were applying 100 millivolts and then we created a 1:10 ratio and we were applying a 10 millivolt signal effectively going into the base of a transistor. That's a small signal. Okay, so in order to set the operating region and hence the operating point, we apply DC voltages. DC voltages are set or applied to our devices, and the procedure is known as biasing our device or biasing our circuit. So biasing is basically the application of an appropriate DC voltage to generate an appropriate DC current based on our application. Now, if our application is, if our application is to use the BJT as an amplifier, then we wish to bias it in the active region, right? In the active region, not in saturation or cutoff. Active region is right here. So if you wish to bias it correctly to work as a function as an amplifier, we would select our Q point or operating point to be somewhere in the middle of the active region. The middle of the active region can be obtained from our value of VCC, right? VCE is our output. VCE is our output, and IB is our input. So if IC and VCE are our output, we want the Q point to be somewhere in the middle of this active region. If VCC is 5 volts, we want VCE to be about 2.5 volts. If VCC is 20 volts, then we would want VCE to be about 10 volts. So somewhere in the middle. Hence, VCE equals half of VCC. The load line process does not change. Like biasing, we want the bias to be in the center. If you analyze it graphically using load line techniques, then the load line techniques, the steps remain the same. They do not change. We apply KVL at both the input and the output side. We apply KVL, we generate our equations, and then we obtain coordinates of the two endpoints to plot that load line. Okay, so the endpoints right here. We have load lines for both the input as well as the output. Okay, input as well as the output. Now, before I begin this explanation, I want to point out something. The author uses a current source, IBB, times RB. Okay, so current source will have a resistor in parallel, and a voltage source will have a resistor in series. So source transformation, you can transform a current source into a voltage source. Whether you use a current source or whether you use a voltage source, the approach remains the same, does not change. If we use a current source, we apply KCL. Okay. If we use a voltage source, then we apply KVL. The end result is going to be the same. We'll obtain this exact expression. So on the input side, you have a current source IBB going in. Some of it goes down RB, some of it goes into the base. So IBB, the source, is divided across the resistor RB and the base current IB. So we obtain the equation for IB as IB is equal to IBB minus IRB. IRB is the current flowing through here, which means it's VBE over RB. If you apply KVL, you obtain the exact same expression, no difference. Once we have this equation, we have two known quantities and two unknown quantities. IBB or VBB would be known to us, RB would be known to us. IB and VBE are the two unknowns. So if you want to find the input voltage and the input current, we plug in one coordinate value as 0, and you find the other value. Once you have those values, you would find the coordinates on the x-axis and the coordinates on the y-axis, and you can join the line, thus obtaining the load line. Same process on the output side. On the output side, you have VCC divided across the resistor RC and the collector to emitter voltage VCE. So VCE is equal to VCC minus ICRC, or we can write IC is equal to VCC minus VCE or RC. This is the equation that describes the line. To find the two coordinates, plug in zeros, and you obtain the output points. One point is here at the bottom, VC is equal to VCC, which is 15 volts. The other one is here at the top, 40 milliamps. Once you have these two coordinates, you join the line, and then the desired point of operation is where we obtain our Q point. Okay, so this load line biasing and operating point is pretty standard. Now let's look at example. Let's take a pause before we do that. Any questions? Any questions at all? Okay. So before we look at the example, let's look at what small signal amplification means. Okay, we saw the large signal model. We're gonna this is not a model, this is of course just an explanation. So in the lab, we applied we connected DC source and we applied DC voltages to our circuit, like BJT circuit. So if we ignore these second, we're applying DC sources VBB and VCC on the input and the output side. And these voltages are going to cause a voltage drop and a current to appear for those resistors. All right. So in general, DC is represented with uppercase notations, where the quantity V and I are uppercase, and the subscripts are also uppercase. For AC, we use lowercase. Quantities as well as subscripts are both lowercase. And if you want to describe a quantity that comprises both of AC as well as DC components, then we use a mix, lowercase and uppercase. And this is standard accepted practice. This is something you should definitely be aware of. Okay, if you see something like this, you should understand what it's trying to say. Now, having said that, not all authors or everybody follows this convention. In our book, what the author is doing is representing any change in the applied voltage or current as a delta, just to show that it's varying or it's changing. There's a change in the input voltage, there's a change in the output voltage, input current, output current. Okay. But for explanation purposes, understand that these are DC quantities and the ones with delta are AC quantities. Okay. Nothing else has changed about the circuit. Nothing has changed about the analysis. The only thing is every quantity now has a DC component as well as an AC component. Okay. So in order to find the biasing points, we would apply KVL at both the input and the output side. When you apply KVL at the input side, we would have VBB, IBRB, and VBE. Now we have an added AC component. So on the input side, we have a small AC signal that is represented by the delta VBE. So this VBB is from our DC power supply. This delta VBB is the signal that you obtain from the function generator. And I'm referring to the lab experiments that we performed. Okay. Again, this VBB is the DC power supply. And this is the function generator sine wave AC signal that we applied. So DC plus AC, DC plus AC, DC plus AC. The format of the equation remains the same, except we now have an AC component. If we talk about just the Q point, meaning if you're talking about just the Q point, we are referring to only DC voltages and currents. That means there's no AC on it. We're ignoring the AC. We have the exact same equation. VBB is IBRB plus VBE. If we subtract or if we remove the DC from there, we can write AC is equal to delta VBB is equal to delta IBRB plus delta VBE. Exactly the same equation for DC as well as AC. And so if we change or rearrange the terms, we can obtain an expression for delta IB. Okay. The AC component of the input current, delta IB, is given by delta VBB minus delta VBE over RB. The same manner, if you apply KVL at the output, we obtain VCC is equal to ICRC minus VCE. Again, IC has a AC component, and so does VCE. Keep in mind, on the output side, VCC is simply a biasing voltage. We are on the input side, we have VBB and delta VBB because we are applying DC voltage as input and the AC input voltage. On the output side, we are simply biasing the circuit. There is no AC component to it. Hence, it's just VCC. There's no delta VCC. Does that make sense to everyone? All right. So then we rearrange the terms and we obtain the exact same expression for delta VCE. Delta VCE would be the change in IC, the output current, as a function of RC. And delta IC can be replaced as beta times delta IB. Delta IB from here can be plugged into this equation. And when we do that, we obtain this equation right here. Delta VCE is beta times RC over RB times delta VBE minus delta VBE. Okay. Any change in the input will result in a change in the output. Okay. If AC input signal is 0, then output AC signal is also 0. The only thing we obtain in the output is pure DC. Does that make sense to everyone? Okay. And you can see the biggest drawback of this circuit. The output voltage VCE is dependent on the transistor beta. Beta is the current gain, but it varies wildly for the same model transistor by the same manufacturer, manufactured and fabricated at the exact same time. Beta values, if you recall from the spec sheets or the data sheets, can range from 35 to 200 for our standard 2222 transistors, or even 3904s. Okay, so you could have two transistors in your lab kit. One of them could be 35, the other one could be 200. Your circuit might work for a beta of 35, but if you plug in a transistor with beta of 200, it's now not in the active mode, it's now in the saturation or cutoff. And so obviously this is a very simplistic circuit with a simple biasing resistor on both the input and the output side. But there are many other factors that we need to account for, which are not accounted for in this circuit. Nevertheless, let's perform an analysis and see what we can obtain in the output, right? So we have one base resistor, one collector resistor, biasing voltage VBB, biasing voltage VCC on either side. And then we have an AC input signal V in of T, V in of T. The input characteristic and the output characteristic are already given to us. We wish to plot load lines and then determine the output for a given input. Okay. As an example, this is not required to determine. This is just extracting as much information as we can from the given data. So the given data on the output side, we can see for an input IB value of 10 microamps, output collector current is 1000 microamps. 20 microamps gives us 2 milliamps, 30 microamps gives us 3 milliamps or 3000 microamps, and so on and so forth. Beta value is consistently 100, 100. This, of course, is idealized. Right? This is an idealized characteristic. Okay, so you apply input, we apply KVL at the input and the output. We obtain our expression V in, VBB, VRB, and VB, 4 voltages. And we obtain an expression for IB and VBE. Right here. V in of T plus VBB is IBRB plus VBE. Out of these 4 quantities, these are known. The only unknowns are the base current IB and the base emitter voltage VBE. Okay, VBE and IB. This is basically, this equation describes the line that we're going to plot, meaning it's describing the load line. We have 2 unknowns in there. To determine the values of those 2 unknowns, we plug in the coordinate values as 0, 0. If VB is 0, you obtain a value for IB. If IB is 0, you obtain a value for VBE. Once we have those 2 values, it'll be somewhere over here and somewhere over here. We join them together. The intersection point be the Q point on the input side. Okay, again, load line analysis, standard approach, no difference. On the output side, when we apply KVL, we obtain VCC is equal to VCE plus ICRC. Again, we want to plot the output load line, so we need the coordinates. Plug in IC is 0, VC is 0, and you obtain these 2 values. Down there and down there. Join them together, we obtain the load line on the output side. Let's take a pause. Let me know if you have any questions. Any questions? Okay. Let's look at an example. All right. Given information for the previous circuit, we have VCC as 10 volts, VBB as 1.6. Resistor values RB and RC are given to us. V in of T is given as 0.4 volts peak value, frequency of 1 kilohertz. Describe it as 0.4 sine omega T. Omega is 2 pi F, hence V in of T is 0.4 sine 2000 pi T. So we need to determine the value of VCE using load line analysis. Okay. Now, we know from the previous slide that the equations both on the input and output side for IB, VBE, VCE, and IC. Right, so we know that from the slide. So what we're going to do is this time we're going to insert V in as part of our calculations, right? If we are talking simply about DC, then IB is equal to VBB over RB. If V in is 0, meaning it's either we are not applying AC or it's at the midpoint right here, then it's simply the DC or the Q point, right? So let's talk about that first. If V in is 0, then IB is simply VBB, which is 1.6 divided by 40K. So you get 40 microamps. And then VBB is 0.6, sorry, 1.6, which is here. One endpoint of the load line. Here is the other endpoint of the load line. 40 microamps and 1.6 volts. When we join these, we get the load line or the Q point without any AC applied signal. The intersection point IB is 25 microamps. We can extract VBE also, but we don't really care what VBE is. Okay, VBE at the Q point is somewhere around 0.6 something, but we don't really care. It does not affect our output. That's what I'm trying to say. Sorry, not that's the wrong choice of words. It affects the output, but it's not required for us to determine the output. So that's why we don't care what value for VBE is. What we care about is IB. Okay. Now, let's say we apply this input signal, right? So it's moving from 0 to plus 0.4, down to 0, and then minus 0.4 and come back to 0. So maximum would be plus 0.4, minimum would be minus 0.4, gives us a corresponding IB value of 50 microamps and 30 microamps. The corresponding VB value for 50 microamps is 2 volts. And then for 30 microamps, it's 1.2 volts. Again, 50, 2 volts, and 30, and 1.2. So if you plot that load line, 2 volts and 50 microamps, your load line has now shifted up. And when V in goes in the negative, meaning the negative half cycle, it causes a drop in VBE. You get it 1.2 volts and 30 microamps. So now your load line has shifted down. In both cases, they represent, this is the max, and this is the minimum. Okay, max and minimum. And at each point, it intersects the characteristic curve. And so we obtain the max value for IB and the minimum value for IB as 35 and 15. 35 and 15. Okay, The input current varies from 35 to 15 microamps. And let's take a pause. Let me know if you have any questions. Yes. You're talking about the Q point? Yeah, the Q point is approximately 0.6. Even if you try to find it from graphically, it'd be kind of like an inaccurate value. But this, again, remember, the load line analysis are giving us these values right here to plot the load lines, right? So these values and these values on the X and Y axis. Once we join these points, they will intersect the characteristic curve in these three places. And we are interested in the value of the Y coordinates of these intersection points, because those Y coordinates represent the values for the input current IB, the base input current IB. Does that make sense? Okay. All right, let's go to the output now. So ignore the diagram for now, okay? There's a lot going on over there. All right, so what we want is we want to plot the load line on the output side, okay? So load line for the output side, you apply KVL, you obtain VCE is equal to VCC minus ICRC. This is the load line equation, the output side. To obtain the 2 points, we plug in one of the coordinates as IC is equal to 0, VC is equal to 0. We obtain VCE is equal to VCC, and IC is VCC over RC. VCE is equal to VCC is this point right here, 10 volts. And then IC is equal to VCC over RC is this point right here, 5 milliamps. Once we have those 2 points, we join the load line. Okay. We join the load line. Once you join the load line, it is going to intersect all of these output curves. Right? Every single output curve, this is for 5 microamps, by the way. Every single output curve is a data set representing the value of IC as a function of VCE. Sorry, IC as a function of VCE. Again, this is the output, right? Output collector current as a function of the collector emitter voltage, VCE. And each is a data set for every single value of IB. Right? We have so many values of IB. But we are only interested in 3 values of IB, which is 15, 25, and 35, which we obtained from here. So we take these and we translate or map them to the output side. And so they are right here, 15 microamps, 25, and 35. So where the output load line is intersecting all of these curves, we are only interested in these 3 points. And the coordinates of those 3 points is the solution to our amplifier problem. Coordinates, the Y coordinates gives us the value of the current, or collector current. And the X axis values are the answers to VCE. So let's take the Q point where it's equal to 0. IB is 25 microamps. The X and Y coordinates are 5 volts and 2.5 milliamps. Minimum value for IB, you get VCE as 7 volts and IC has 1.5 milliamps, and then maximum value, which is at 35 microamps, gives us 3.5 milliamps and a VCE of 3 volts. And that's how we find the values or the solution using load line analysis. Let's take a pause. Let me know if you have any questions. Any questions at all? Okay, let's talk about the diagrams. Okay, so we have 3 values. We have the Q point value for IB, we have the minimum, and you have the maximum value. When IB is at maximum, meaning at 35 microamps, translate to this point, and the corresponding IC value is 3.5 milliamps. So when IB is maximum, IC is maximum. But when IC is maximum, the corresponding VCE value is at a minimum, 3 volts. When IB is at the Q point, IC is 2.5 milliamps. Corresponding VCE value is 5 volts. When IB is at a minimum, which is 15 microamps, your IC is also at a minimum, which is 1.5 milliamps. However, your VCE is at a maximum, 7 volts. So input voltage increases, meaning VBE increases, then IB increases. When IB increases, IC increases, but when IC increases, your VCE decreases. That's inversely proportional. Hence, you obtain a waveform that is 180 degrees out of phase with the input signal, or as we say, it's an inverting amplifier. And that's the reason we get an inverted output. And we saw this in person when we performed labs 3 and 4. We had a 180 degrees inverted output. Does anyone remember? Vaguely. This is the reason why. Also, our input is at 0 volts, which is right here, right? Input voltage current does not have any DC component, but our output has a DC component of 5 volts. Remember, the ground line or the center line for our output is at 5 volts. When there is no AC input, meaning when AC V in is 0, your output still is a value of 5 volts. And so everything is shifted up. Okay, there's an added DC component of 5 volts right there. And this is drawn straight up, so it's 5 volts. And hence we apply a bypass capacitor at the output or a coupling capacitor at the output, and it blocks this 5 volts and brings it back down to 0. Okay. All right. This is actually, this slide is where I stopped for the other section. So I'm going to end class here today for this one. Still actually have about 10 minutes left. We went a little bit slower in the first one. Okay, we'll pick up here again on Monday, and then we'll cover a little bit more extra in the, in those 25, 30 minutes. And then by Wednesday, we should get all caught up. Yes. So quiz on Monday will be based on BJT fundamentals, short answer questions, which I didn't assess last week a lot. And then perhaps load line analysis, what we are doing here. I will set homework. The homework will not be due on Sunday. It'll be due most likely like Tuesday or so. Students have some breathing and then we'll pick up the pace again next week. Not quite, no, not quite. All right, have a good weekend. I'll see you all Monday.